All right, and now I can start. Today we will learn about like the concurrency bugs and deadlock. So like we will move one step forward on top of like the mutex and then lock primitives. And then one thing to notice that there will be no videos Zoom sessions next week because we will have a quiz 3 on November 22nd, and then November 24th is Thanksgiving Day. So please have enjoy the time with your family. Yeah, and then like we will have quiz 3. So quiz 3 will be open from like November 18th, the Friday, tomorrow, and then it will be open until November 28th, so that you can use it any time in between these days to take quiz 3. And then we will do the same policy, open material, and 3 times available, and then I will take the highest score. Then question. All right. Right. Then what I can do is make it as this and put it on this side. All right. Yeah. All right. And then the quiz 3 will cover the most part of the multi-threading, synchronization, log and thread synchronization. So the thing we learned about the mutex and their implementation. And also it will cover the material that we will learn today about the concurrency bug and deadlock. And then one question from Zoom side is like how far through the lab would you recommend we get before taking the quiz? So for the lab contents, so like I do not ask like the 2 specific questions from there, but if you follow what we are doing in labs conceptually, then I believe you can answer the question. So it will ask a specific data structure and how it is being used. But if you finish lab 3, then like you will have no problem. But if you haven't not finished lab 3, then you can refer to the code and then lab description material to answer the question. And then for lab 4, because we are not there for finishing lab 4, so I will not ask like the 2 difficult questions in there. So you don't have to worry much about like the lab 4 part. And to learn little about like what kind of questions will be there for the quiz 3, you can refer to the sample quiz that I distributed in like the 2019. So the questions would be different, but within that will be within the similar category. So like you can feel about like what kind of questions will be there. Any question for quiz 3? All right, then I will move on. So we learned about from last week, we learned about the data race example. And then, so the data race happens if 2 or more thread write on the shared same data. So in this example, the shared data was the variable counter. And then the data race happens if the load of the variable and then store of the variable are running apart. And in the middle, if the nether thread, if there's a chance that the nether thread can load the value, then they will not see the updated value here. So it will result in like even if the both thread increment the counter value will be resulting in like the increment just 1, not 2, because of like this kind of the data race example. So it's something similar to the how we move forward in the stop sign junction in reality. So the case is something like this kind of thing. And then if we implement lock and unlock correctly, then we can control this kind of the traffic to pass one car first, and then the other car pass later, then there will be no accident. So you can think it as like the data race case is something like, so one car gets into the junction, but it has not finished to the crossover the junction, but some other car gets in, and then crash happens. So the reason why I like bring this kind of crash example is like so if we just use the data and code, it looks like just tainting the data and then changing some of the variables, but that actually make an impact that the program could crash or a program can go wrong, so that would be regarded as similar to the real incident in reality. And to control this kind of the junction with the proper doors, lock and unlock, so we learned about the concept called mutex. And the mutex is for mutual exclusion. And then what we are doing is that for the part that we need to update the shared data, but if the load and store, so load is here, and then store is here. So if these are apart, then what we can do is we can create a critical section that only one thread can enter and execute using mutex. And creating a critical section with mutex is quite simple. So if you can identify the code that might have data race, then you can wrap it with the lock and unlock. So you will place a lock at the entrance of the code that may suffer data race, and then you will put unlock at the end of the execution of the writing the shared variable. And then how it works is, so suppose thread 1 runs first, then it will acquire lock and then get into the critical section and then try to run on the instructions here. But at that moment, if some other thread gets in, then because this lock works as guaranteeing that only one thread can execute in the critical section, so it will make the thread 2 wait until this thread calls unlock. And then that is done by setting a lock variable, and then this thread 1 put number 1 to indicate that the lock has been acquired. And then thread 2 is keep waiting in their own while loop. And then if the thread 2 calls unlock, then that will make the lock variable to be 0, and then that is visible to thread 2, then they can continue to run. And then it will happen every time any kind of thread gets into the critical section. So suppose the thread 1 try to acquire the log again, then they have to wait until the other thread finishes and calls unlock. So this is the semantic of the lock and unlock. And then if we implement it correctly, then we can synchronize all the thread, and then we can get the consistent result. And then we can remove any kind of the data racing between these two threads about these 4 lines of the assembly line. So it works like that. And then conceptually, we can implement that in software. And then the first thing that I tried in our example was I created a Deadlock. So how Deadlock works is, so it will get into the while loop and then wait until lock variable becomes 0. If that is 1, then it will spin in the while loop. Then after observing 0, then it will exit the loop. And then immediately after that, set the variable as 1. And then unlock is setting the variable as 0. So if one thread set the lock variable as 1, then all the other thread should not pass this while loop. And then immediately after that, we set the lock variable as 1. But yeah, and then at the end, we release that by putting the value 0 to the lock variable. But the problem of this approach is that these two parts, running a while loop and then writing a lock, is not atomic at all. So that could be separated apart by with some of the instructions. Then there would be a chance that some other thread or process can intervene the execution. So because this is reading up the lock variable and then setting up the lock variable is not atomic, not one single instruction. So there is a chance for data racing. So this is how the value has been loaded. And then this is how the value has been stored. And then we are seeing the 4 number of instructions. So we are getting back to the same example of the counter. So with the pure software manner, we learned that we cannot resolve this kind of issue because, so in the ideal case, we would like to see that the thread 1 runs like observing log is 0 and then set it as 1. And then the other thread wait on like the lock variable as 1. But how it could be executed is something like this. So if the thread 1 observes the lock variable become 1, then while they are executing in these 2 instructions, some other thread can get in and then run about the first instruction to load the lock variable. Then the 2 or more thread can get into the critical section, so that this implementation is not conforming to the guarantee that the lock should make. So that's the problem. And then because like the instructions are not atomic, so to implement the correct lock, we need to rely on the hardware primitives that guarantees that the update and then checking of the value is atomic, and then no other processor thread can intervene on it. So in the Intel x86 processor, there is an instruction called exchange, and then we categorize that instruction as a test and set instruction, because what it does is like it will read the value and then update the value with a single instruction, and then we can test that later. So we can actually do the getting the value and then setting the value at the same time. But conceptually, we will read the value to test it, and that's why we call it as a test and set. And this exchange function, what it does is like that if we place the lock variable pointer and the number 1, then it will execute exchange instruction and then read the value from lock variable and then put that onto the result. But the result will be putting it as a EAX register marked as A. So that means that it will be put on the return value. So what it will do is it will write 1 to the lock variable, but before making the write, it will read the value and then return the value as a function return. So if we observe 0 at here, that means like a previous lock variable value was 0. But at the same time, it will be updated as a 1. And then because this instruction exchange is guaranteed by the CPU that no other processor can intervene, so atomicity is guaranteed. Yeah. So this is where we are actually making test and set. So the exchange itself does like the read and update, and then actual test happens in while loop. But because the read and update is atomic, then there's no data race. And then we can also see that this exchange instruction for reading and update the variable is just a single instruction, and that's why it cannot be intervened by other execution. But there was a problem in using exchange, because we will always update the lock variable to 1. So even if the previous value was 0, then we need to update that as 1. And then even if the previous value is 1, we also need to make a write request to update the value. And that actually incur a lot of like a cache invalidation to the other CPUs. So in our example, if we run the exchange example with the 30 threads, then we will observe a lot of cache misses in there, and that affects on our performance of the lock. And to avoid that kind of the cache invalidation, by examining that, we can know that. So updating from 0 to 1, that's necessary. But updating from 1 to 1, that is not necessary at all. So the one simple logic is that like one simple workaround for cache miss, reducing the cache miss, is what we can do is like we can ignore the 1 to 1 update case, and then just update the real 0 to 1 update. And to do that, we can write a test and set. And then the first test is to check if the lock variable is 0. And then only if we observe the value 0, then we will update as by 1, the lock variable as 1. But there was an instruction from Intel called compare exchange. That's actually the test and set instruction, but the Intel implemented it in an incorrect way. So it does not work like as expected, and it always update the value. So one of the way to avoid that is like you can implement software version of the test and set. So actually the log itself is guaranteed by this exchange atomic instruction. But before running this, you can check it if like the lock variable has been 0. So this second while loop will be exited when the program will exit from the second while loop when they observe the lock variable value becomes 0. And then they try to acquire lock. And by doing that, we can reduce the number of cache misses by reducing the updating from 1 to 1. So although like the checking of the while loop is not atomic at all, but the real update of the lock variable is atomic with this exchange instruction here. So this is part for the test, and then red one is part for the test and set, and that's why we call it as a test and set. And then the purpose of doing this is like to reduce the number of like the cache misses that is necessary. And you can run all those kind of the implementations, and then you can also edit the implementation with the code so that you can check out the example code in here and then run on the OS2 server. Then you can take a look at how each thing works. And then we also implemented the exponential backup version of the lock. And then what it does is like if the one thread could not acquire the lock, then it will wait for the 1 cycle, the next time 2 cycle, 4, 8, 16. And then there's a mechanism about that. And then that resulted in like the faster performance than the mutex lock. And many of students are curious about like in that case, how the real pthread mutex was implemented and then why the performance differs. Then this is the code that I grabbed from the pthread mutex. So the one good thing about the studying computer science is that like many things are open source. So if you're curious about like some of the implementation, you can go to GitHub and then check their code and then examine how they have been implemented. So this try lock actually checks if the mutex, the lock variable, if it is 0 or not. So if that is not 0, then they should wait. And then they are getting to this kind of the while loop. Yeah. And then inside of a while loop, it will increase the max count as spin count multiplied by 2 plus 10. So in our example, we shift the counter by 1 left. So that's actually the multiply by 2. So that our delay will be 1, 2, 4, 8 kind of that fashion. But in this case, it's more than that. So if the starting value is 1, then that will be 12. And then 24 plus 10 is a 34. It's something like that. So it increases exponentially, but a little different. Yeah. And then I checked this value, and then the default count is 100. So like the sequence will be increasing as a 100. And then like the 210, and then 430, something like that. Yeah. So the important thing is like they are actually doing the exponential backup, but with the little larger number for the waiting time. And then if they observe like if by waiting while waiting after waiting about like exponential backup time, and then if they observe that they can acquire the lock, then they exit the loop and then acquire the lock. But if they fail to acquire the lock, then get into this loop again and then increase this spin number again and again. But there is a cap, so it will take a minimum value of this exponential backup counter and also the max adaptive count. So that's actually similar about like I set the max count as like the 64 kilo, right? So that kind of the adjustment has been also made in the pthread mutex. So what you can learn from here is that like even if our exponential backup implementation looks very simple, but it has all the principles that we are actually using in the pthread mutex in there. And next, so there are problems of lock. So if we use lock, we can control and synchronize all the thread correctly and get the consistent result. But the problem is that log is very slow. And then you will see that there is a while loop. And then if it is just a while and waiting for the others, what's the problem? But the problem is like the computers runs super fast. So it runs several billions of instructions per second. And then this, if you have like a multiple threads waiting for the single lock, maybe have like a 100 thread or something, then you could observe that like the one thread could wait for the lock for several seconds and then wasting all the CPU cycles about that, do nothing, and then just keep like running on the while loop. And then we should avoid that kind of case, because that's just like the consuming all the electricity. And then for that kind of CPU, we don't do anything, just waiting in the log. Yeah. So like there are several ways we can increase the efficiency of the log, not just for changing the log itself. Yeah. But how, by changing how we use the log, we can actually increase the performance. And the case is that like we need to use the log when it is required. So there are cases that we don't need the log at all. And then if we use a log at that point, then that might be like just an overhead. Yeah. So the first thing is that we need to determine when to use log or not. And then, so for making the consistent result when sharing a data on like a multiple thread, so that any kind of write must be finished before the next load starts. Yeah. So suppose the case that we have like the set of the thread. So some of the thread are reading and then some of the thread are writing the data. And then if we have many readers and many writers, so we definitely need to use a log. Because like if one thread before writing the data, if the other thread read the data, then that could be a problem. And then that could be reduced to the case that suppose we have a 2 reader thread and 2 writer thread, but in that case that there could be cases that the having the data race. But the special case is that, so I made a mistake here. So if we have only one writer and then many readers, so in that case, we don't have to use a lock always. So there are like the majority of the cases, we don't need a lock if we just have one writer, because if that write is not visible, then like everybody will not see the write. And then after making the thread making the write, then that will be visible to all the other. So the important thing is like if we have a 2 or more writers, then like we need a lock. But otherwise, if we have only one writer and then just reading the values from among the multiple thread, in that case, there's no update, so we don't need the lock. And then if there's just one thread updating the write, then there is no data contention for writing, so that we don't need the lock. So the important thing is like we need to count the number of the writing thread, and then based on that, we need to determine to decide to use the lock or not. Yeah. So suppose there is a one thread writing the value, and then all the other threads are reading the value. Then there could be a case that like a thread 1 just to load the counter, but that has not updated the value yet. Then thread 2 will see the previous version of the value. And then because this write has not been issued, there's no problem. And then if the case is like the writing thread has finished the load and write, but if the other thread comes in later to read the value, then it will see the updated value of the counter, but that does not have any problem because this thread 2 is just reading. So that's the case, like we don't need the lock. Any question for this kind of the categorization? Yes.
So if the thread 2 reads the old value, so
pardon?
Thread 1 is updating the counter value, right?
Yes.
So why shouldn't thread 2 like get the new updated value?
So if you want to make the result to be like if the thread one, after thread one load and update the data, then that should be visible to thread two. So if you want to make that kind of ordering, then you should use the log. But think about the case that, so thread one will run, and then from the thread two's perspective, if the write has not been happened, then they can regard that the even read has not been happened yet. Yeah. So that if your program can be consistent without making this load and write happened in a single thread, yeah, then like that'll be fine. Because there's no write from the thread two, and then that cannot affect on the execution of the thread one. So, but the important thing is like that not all cases are like this. So that there is some case that we need to make this load and write, load and store need to be in a critical section, but not that many cases are falling there. That's why I'm emphasizing that there are many cases, around the 99%, that like if you have one writer and then many readers, then you might not need a lock. Yeah. And then the first thing is like we need to determine whether the log is required or not. And then next thing we need to think about to increase the performance of the log is how can we set the critical section? So in this example, suppose we have 4 different data update. So this case it has like we have many writers and then we need to synchronize that. So we have to use the log. And then suppose we have 4 updates in line. Then what we can do is like even if like these are like the independent update, we can create a big critical section like this and then run it. And then that means while the thread 1 is running execution on the thread critical section, then another thread need to be wait and then waiting. And then after critical section execution finishes, then they can run. So thread 2 is actually wasting the time for waiting this amount of the time, right? Yeah. So this case, so in case like if like all these kind of updates are independent, not depending on the previous update, then what you can do is like we can create a smaller critical section per each one. So instead of using a big critical section, having a 4 update in there, we can separate it as like the 1 update each as a critical section. And then when the thread 2 wants to run on it, then we can order it like a different order than like they can, if the critical section A was like taken by thread 1, then we can schedule the thread 2 run on the different critical section first. And then by crossing it, like we can let the other thread not wasting the time run on the independent critical sections. Any questions about like splitting the critical sections into smaller pieces? But doing this is beneficial, but we are not doing this in all cases because to do this, we need to analyze the data dependency, and then we need to identify what are the independent write or read. And then after analyzing that, we need to place the lock correctly. So developers must take care of like the conditions that they could have like this race conditions, and then they need to be sure about like the splitting critical sections like this. So in doing this, there could be a lot of cases that the developers make mistake. In that case, it will be resulted in an inconsistent result, or it could be resulted in a deadlock, which we will learn at the end of this lecture. So deadlock means like the CPUs are all waiting for the lock and then do nothing. So that we want to avoid that kind of case. But if we write the big critical section like this, so it's quite easy to manage. But if we try to splitting the critical sections into the multiple pieces, then the complexity goes up. So that's why like not all locks are splitted in this way. Yeah. So in ideal case, if we can identify all the data race conditions and then split the logs like that, then that will be the perfect for the performance wise. So the general practice is that, so the first thing we learned about we need to determine whether we need to use a log or not. So we need to use log only if it is required. Yeah. And then another thing is like that to increase the performance, we can use a smaller critical section to let the other thread working on something else while waiting for their getting into the one critical section. Yeah. So these looks very simple, but sometimes it's very difficult. And then let's learn about why it could be difficult with some examples. So this is an example taken from our textbook. And then there is a data race condition bug. And then can you identify what would be the bug in this code? So thread 1 reads the thread prog info here, and then use this variable. And then thread 2 sets a prog info as a null. Yes?
Thread 2 may update the value and the F.
Right. So after thread 1 execute this line, suppose the thread 1 is at here, then if the thread 2 runs this line, then this pointer will become null. And then outputs will dereference the null pointer. Yeah. So this is so-called time of check to time of use bug. And then the reason why is, so thread 1 will check the validity of the variable. So that's the time of check. And then time of use is using that variable in outputs. So in single thread, there's no bug at all. So we already checked that that variable is not null. And then we can, based on that, so we can use the pointer because that should be not null at all. But the problem is that because we are in a multi-thread environment, so that this write can happen in between the time of check to time of use. Yeah. So in that case, this variable become null, and then we can result in a null pointer dereference, and then program will crash. So logically, so thread info should not be null here, but after passing the if condition, there could be a case that the thread 2 can update that as a null, then there is a null pointer dereferencing can happen. Yeah. Then how can we resolve this kind of the concurrency bug? So the simple solution is like we can use lock. Yeah. So what you can do is, so all the data race conditions are happening because like a read, write, that kind of ordering is not done very well. Yeah. And then to resolve this kind of the time of check to time of use, yeah, what we can do is like we can have all the data reads or use of the data in a single critical section. So from thread 1, what we can do is like before checking and using the variable, we can create the lock called the prog info lock. Yeah. And then acquire the lock before checking the variable and using the thing. And then after processing everything, we run unlock. And then in thread 2, we will create the critical section with the same lock, but we will execute a different one. But in this case, we will update the thread info variable as a null. Then how the execution will go on is, so suppose thread 1 executed first, because if the thread 2 executes first, and it will say set it as a null, and then thread 1 will not doing anything. So to execute the thread 1, we must acquire this lock first, and then check, and then try to use it. But because it is protected by the critical section, no update can happen. If the thread 2 started execution in the middle of like the time of check to time of use, previously it immediately updated the variable to null. But in this case, because thread 1 is executing in this critical section So they must wait because they cannot hold the lock. Yeah. So that this update cannot happen. So within the critical section, there's no case that the update may happen. So we can avoid time of check to time of use bug in here. So by using lock, we can resolve this kind of the concurrency bugs. So the concurrency bugs are a type of the bug that the code does not have vulnerability at all when it runs in a single thread. So the previous example, we have checked that variable is not null, and then that should be not null. But that there's a case that the another thread get into the execution, and then they can update the variable. So the bug may appear when we run it in a multi-thread, and then or with the multi-process and the multiple cores. Yeah, if there's a shared variable, then this kind of the problem can happen. And for next, we will learn about what types of the concurrency bugs are there, and then we will learn about how can we resolve them. So the first one is about the atomicity. So we already seen this kind of example, the time of check and time of use. This was not atomic. Then that's why this kind of the write can intervene in between. And to resolve this kind of the atomicity, non-atomicity, we need to make it as this kind of the time of check to time of use as atomic. And to do that, we can use the lock and unlock to wrap the entire thing as a critical section, and then create the same critical section for the updating. Then we can guarantee that either one thread can run entire of this piece of the code, so that we can block all the update interfering for the thread one's execution. Yeah. That's what we can do. And then there is another case. So this example is also from the textbook, but the textbook actually grabbed this code from the Mozilla Firefox. So this is from the real code. And then there are like the two type of the function. And then there could be a case that the thread one runs on init and then thread two runs on main. And then suppose the program has been executed in this order. So the thread one, after they create the thread and then store that as a mthread variable, and then sometime later, if thread two gets in, then they can use the thread variable because that has been initialized here. But there could be a case that thread two runs first. So when we fork the thread, we actually don't know which thread goes first. Now, operating systems, they can schedule it. So in lab 3, we implemented a very simple scheduler. Just go over, round over, and then you run it. Yeah. And then in doing that, there could be a case that the operating system do not schedule thread 1 indefinitely, and then just schedule thread 2 multiple times. Then it could run in this order. Then when thread 2 runs, the thread variable has not been initialized yet. So that could be null, or that could be some of the garbage value remaining on the memory. And then that will result in crash. So in this case, we need to order the execution to have the thread 1 must be finished execution before thread 2 continue to run on their own execution. So we need to make the ordering like this, no matter how the operating system schedule the processes for thread. And then we can actually do this kind of the ordering with lock, but we need to use two locks. And then, so this is actually called as a conditional variable, but we do not cover the conditional variable here, but you can regard that as a secondary lock. And then let me explain how it works. So we want to make the thread 1 runs first. And to do that, so after initializing the thread variable, what we will do is we will run lock on the empty lock. So this is just a global lock for this one. And then after initializing the thread, then we will put the empty init value as a 1. And then we will do, what we will do is like we will run the conditional variable signal to the another variable. So even if this is like written as an empty cont, but you can regard this as an empty lock2, so you can regard that as a different lock. So what it does is actually, so it tries to acquire the first lock, and then after finishing their operation, they will release the second lock, and then release the first lock. And then let's follow the how thread 2 works. Yeah. So suppose thread 2 runs first, then they try to acquire the global lock. Yeah, they can get in, but because empty init is not 1, then they should wait at here. And then this pthread conditional variable wait. What it does is it will release the first lock to let the thread 1 can get in, but that they are stuck in the second lock, waiting for the condition. Yeah. So if the thread 2 runs first, then they will wait at here. And then later, if the thread 1 start to run, they can acquire the lock because the thread 2 released this lock. And then after updating the variable, they will signal this variable so that that's actually releasing the secondary lock. So this second thread can bypass this one, break out this while loop, and then so internally it will automatically acquire this log again. Yeah, and then that's why we have a lock here. So it's something like, so to make the thread 1 runs first, so in case if the thread 1 gets in first, we make the thread 2 wait for this kind of the releasing of the secondary lock. Yeah, and then only if after thread 1 release the secondary lock, then thread 2 can proceed. And then this is the technique that using the 2 locks. This is the technique that we can order thread 1 and thread 2 always running in that sequence. Any question about this part? I believe some of the difficult part is understanding about the conditional variable, but you can think it as a secondary lock, and then it has been locked by default. And then this is actually the unlock of the secondary lock. Then thread 2 can proceed, and then we can synchronize the thread. And then there could be a case called the deadlock. So in previous cases, so 2 threads can run, but their results could be inconsistent, atomicity and ordering. But in the deadlock case, so we could observe the case that no thread can make any kind of progress. And then we are actually wasting all the CPU cycle, and then program will never finish. And then the cases like 2 or more threads are all waiting for acquiring the lock that has been acquired for the another thread, and then that another thread is not finishing at all. So the deadlock could be caused by the 2 lines of code simply, yeah. And then suppose we have a lock 1 and lock 2. And then suppose the thread 1 tries to acquire lock 1 first and lock 2. And then thread 2 tries to acquire lock 2 first and then lock 1. Then assuming some of the ideal case, because if there's a one case of the failing, then our logs fail. So suppose those 2 threads are running on a different CPU core at the same time, then we can regard that both of them just finish it up like acquiring lock 1 and lock 2 respectively. Then what will happen is thread 1 hold lock 1. And then thread 2 holds lock 2, like this. And then the next line, thread 1 would like to acquire lock 2. And then thread 2 would like to acquire lock 1. But the problem is that the lock 1 is already acquired by thread 1. So they should wait until thread 1 finishes. But the thread 1 would like to acquire lock 2. But that is already acquired by thread 2. So they need to wait. So this is the case that the thread 2 waits for log 1, thread 1 waits for log 2, but both of them are not releasing at all. Yeah. So this case is something similar to when they are facing the data racing. So they are very greedy. They want to go forward first. So the ideal case, it should be passing like build the others and then let them pass, then they can move. But this case is something like everybody wants to go so that nobody wants to make progress. Something like this. Yeah. So that this is the deadlock case. So the previous example of the deadlock was a very simple one. So if we have the 2 locks, but the threads are acquiring in a different order, yeah, then there could be the case that thread 1 have acquired log 1, thread 2 acquired log 2, but if they try to acquire different locks, then they cannot do that. Yeah. So this is because like if we have a circular dependency on like this kind of the log acquiring between the thread and locks, then there must be the deadlock. Then what's curious is like how can we resolve this kind of the circular dependency? So circular dependency happens because thread 1 acquired the log 1, and then at the same time, thread 2 acquired the log 2, and then wait for log 1. Then thread 1 waits for log 2. So they are acquiring different locks and then waiting for the different locks. So that happens the problem, that causes the problem. So one easy way to fix that is like if we make the order of the acquiring lock consistent across all the thread, then there will be no circular dependency. So let's check about that. So the previous case was like L1, L2, L2, L1 in each thread. And then the new case is like they always acquire L1 first in both thread. So in the previous case, so if we assume that the first line has been executed by like each of thread 1 holds log A, log 1, and then thread 2 holds log 2. And then after that, they are trying to hold like each other's log. That's why it has been stopped. But if we order this kind of thing perfectly, then suppose the thread 1 started first. They can hold log 1, and then when the thread 2 gets in, they should wait until thread 1 releases log 1, so that they cannot acquire log 2. So thread 1 can acquire log 2 after that. And then after thread 1 finishes and then running on lock, then thread 2 can run. Yeah. So that by ordering the log acquiring order, we can remove this kind of the circular dependency, and then let the thread move forward. And then I just explained about like the case that the thread 1 goes first, but if thread 2 runs first, and then you can switch thread 1 and 2 in the diagram, and then the result will be the same. So any questions about like resolving this kind of the circular dependency for the deadlock case? So this looks very simple because we just use 2 locks, but there could be a case that we are using 4 or 5 locks at the same time in a complex code. And in that case, like ordering all the locks could be difficult. And we will see why that kind of ordering is difficult. So if all the locks has a number, log 1, 2, 3, 4, 5, then we can call it by the numbers, right? But that cannot be possible in the code. Then let's see the next example. So we are using many data structures in doing programs. So stack, queue, list, tree, array, all those kind of things are data structures. And then we just learned about the data racing and concurrency issues. And those data structures need to be so-called thread safe to be used in a multi-thread environment. So think about it. If there is an array, so array is managed by like the vector in C++, then internally, whenever we add the item, it runs a lot of code. So the adding the item is actually the writing to the shared data structure. And then there could be many other threads operating on the same vector, then there could be the data racing. And then the example in this code snippet is that suppose we have a set data structure, and then we have two sets, S1 and S2. And then what this function is doing is like try to get the set intersection. And how it runs is like that it will create a new set variable, and then going over all the items in the set one, try to find that is existing in set two. And then only if like the set two has the same item, then we add the value to the return value set and then return it. So it's very simple data structure. And then to make it thread safe, what we can do is like per each of the set object, we can create the lock variable. And then before operating anything from the set object, we can acquire mutex lock for the set one and set two. And then after running all these things, we can release the set two and set one lock, and that's it. And then from the previous case, we learned about that we need to order all the lock acquiring sequence to be equal to all the other threads. So if we require L1, L2, L1, L2 for all the other threads, then there will be no circular dependency. But if the order was mixed, then there could be the case for the circular dependency. So that's why in this example, I put the lock order S1 first, then S2. And then in this code, I hope that this will create a critical section and then having no data race issue at all. So for example, there are several other set operations. So like I want to make sure that while one of the threads running in this set intersection, no other threads are updating the value. If, for example, if the another thread update the set two to insert a new item, then the result would be like totally different. So the important thing, so I remove the unnecessary part, and then we are focusing on like how we create the critical section. And then suppose we have two threads. Thread one runs the set intersection on set A and B, and then thread two runs the set intersection on A and B. Then how they will acquire locks in this code looks like this. So they will acquire set A lock first, set B lock later, and then do the same thing on thread two. So because locks are ordered perfectly like this, in the same order, there will be no circular dependency, which is good. But actually, this implementation is not thread safe. So can you guess like what kind of case would be the thing that it will create the circular dependency? Yes?
If for the two threads, you just swap the two arguments of the sets.
That's right. Yeah. So even if we make the S1 first, S2 later, and then makes this kind of order for like across all the thread can choose this kind of variable freely. So what that means is that, so suppose we have this function, and then we will always acquire S1 lock first, and then S2. Then suppose the thread one calls the function as a set A and B, and then in the another thread, we can call it as a set B and A. So let's run on the same code again. So S1 lock first, S2 lock later. So on the first thread, our lock acquiring order is for like a set A first and then set B. But because in thread two, we put set B as S1, so it will require B first and then A. Then it creates a deadlock. So even if we learned about like if we can order all the log acquiring order across the multiple thread, So then we can resolve the deadlock, but that cannot be done in the code and the variable manner. Yeah, we need to actually order the locks regardless of like this kind of the variables are mixed or like swapped like that. Yeah. So this is a difficult problem, but there are principles that we can avoid this kind of the deadlock. Yeah. And then so researchers have been defined that like at what conditions can cause deadlock, and then these are just 4: having mutual exclusion, having hold and wait, having no preemption, or having a circular wait. Yeah. And then if deadlock happens, what we need to do is like if we need to identify where it happens and then try to understand the cause of the deadlock falls into the which category. And then after identifying that category, we can use the predefined manner to resolve that. And then let's go over like each of the cases, and then like let's learn about how we can resolve that. So the first thing is like if there's a mutual exclusion, then there could be a deadlock. Yeah. And then if there's a data race, then we have to use mutual exclusion. So that this seems like somewhat contradicting because we have to use mutex, but if there's a deadlock, they say we should not use mutex. That's ironic, but that's not the exact meaning. Yeah. So if there's a mutual exclusion based deadlock, yeah. So if the deadlock happens with the single log or something, then it is recommended to not to use log if it is possible. So if it is not possible, we need to handle that in a different case. But what that means is that so that we can replace the lock. So the lock has a exchange and then while, right? So that we can replace that into different atomic primitives. Yeah. So what that means is that like we learned about the compare and swap, and then what it does is like it will compare the value with the sum of the expected value, and then only if the value is matched, then it will update the value. So how we can do that is recall the example that we increment the counter value by 1 by 1. So that's actually can be implemented this add function. Suppose the value is the target counter that you need to update, and then amount is just 1. And then to make that consistently running, we can use a mutex lock like this. But here, what that means about like the do not use lock is that, so instead of like doing this, we can actually write this kind of lock into like the compare and swap instruction. And then what it does is like it tries to read the value first. And then what we want to do is like if we want to store this value plus amount. And then only if the previous value is the same as the old value, that means there's no update from other thread, then we update the value. So the difference between this and this case is that, so when we use log, then some other thread would like to use the log again, yeah, and then there could be the case for the deadlock. But in this case, so it's very similar to log. It has a while and then compare exchange, but what it does is like it guarantees that at certain moment, at least one thread can update the value. Yeah. So the deadlock is the case that no thread can make the progress. So by doing this, so there's no case that no other thread can make progress at all. Yeah. So that's the meaning of like removing mutual exclusion, removing the lock into the different primitives to running on the same operation. And then the next case is so-called hold and wait. So the hold and wait is very similar to the case of the similar to the circular dependency. So if one of the thread hold the thread set A lock, and then try to acquire set B lock, but because they do not release the set A lock, so all the other thread need to wait until current thread hold both of lock. But these two locks are totally independent. So if we cannot acquire set B lock, then it'll be better to release the set A lock and then wait again. Then like the other thread can hold the set A lock, can work on it. So to remove this kind of the hold and wait, what we can do is like we can create another lock. That could be an umbrella for all the other locks. So for example, if we have to acquire two different locks at the same time, then we can create a meta lock for creating a new critical section for acquiring the lock. Yeah. Then what we can do is like we can wrap it, locking up the lock 1 and lock 2 with the meta lock. Then all the other thread who wants to run in this lock, yeah, they need to pass the meta lock. And then this meta lock guarantees that the acquiring of the lock 1 and lock 2 can only happen by single thread, one thread. So there is no case that the lock 1 has been acquired by one thread and the lock 2 is acquired by another thread. Yeah, there's no case like that. So by using this kind of meta lock, we can order the lock acquiring, and then we can suppress like all the interference from the other thread. So the previous set intersection example, we can resolve that by having a meta lock. So think about this kind of case. And then, so we have a meta lock here. And then think about the case that the thread 1 runs a set intersection with the set A and B. And then thread 2 runs a intersection with the B and A. So even if their lock acquiring order is mixed like this, because there's a meta lock, if the thread 1 runs first and then thread 2 must wait until entire thing has been finished. Or otherwise, if thread 2 runs first and then same thing happens. So there's no case that the thread 1 can acquire set A lock, and then thread 2 acquire set B lock, so on. So the one easy way to like make the data structure to be thread safe is you can have like this kind of a meta lock for the data structure, and then like block it every time. Yeah. So that could be the one of the way that like you can remove all this kind of the deadlock scenario in using multiple locks. Yeah. And then this will also guarantee that because it will run as a meta lock, so this will always guarantee that the one thread can make the progress. And then another case is so-called no preemption. So this can be also explained by like the same example. So we have the ordering problem, and then A, B, B, A, and then each of thread acquire A and B. Then each are like they are like they're on the circular dependency. Then they cannot move forward. Yeah. So if a thread acquired a lock A, but that they fail to acquire lock B, then all the other thread waiting for lock A should wait until the first thread acquire B. That's the case. So that we previously resolved that with the meta lock. And then another way to resolve this is so that we can release a lock if we fail to hold the entire locks. So what that means is that suppose one thread acquired the lock A, and then if they fail to acquire lock B, then what they will do is like that they will unlock the lock A and then go back to the top. And by unlocking A here, that actually allows the other thread get into the critical section and then move forward. So it's something like, do not hold the sum of the lock and then wait for the another lock. And then if we have that kind of case, release all the previous locks and then do entire thing again. So that's the way that we can avoid the deadlock. And then the last case is like a circular dependency. And then using the same example, we can resolve the case. And then like the problem was like if we have like a different order for each thread for acquiring lock, that was the problem. So the one of the ways like we can make it synchronized, like it always call log1 and log2, log1 first and then log2, so that we can make that kind of ordering in the code. But we have seen that this kind of the ordering in the code is not sufficient because like the variable names, so functions could be like called as a swapping the variables. Yeah. And to avoid that kind of issue, we need to have a total ordering of the log variable. And then we can actually do that. So how we can do that is, so the log variable here are all pointers. It's just a pointer to like a integer variable. And then if that integer is 0, log is open, that is 1, then log is closed. Yeah. And then when we are running multiple thread, we are in a same virtual memory space. And then think about we are allocating logs in the memory. Each of log will have a unique memory address, and then they are not duplicating, and then those values are comparable. So what we can do is, so we can always check the address value of the log variable, and then acquire the bigger address first. Yeah. So in that case, no matter how you swap the variable or something, we can guarantee that because the log variables are uniquely stored into the different memory location. So we can always have a single ordering for acquiring log by doing this. Any question about the last part? So even if we swap the variable, the ordering of the address will not be changing, so that we can use that kind of the total ordering of the log variables to make the always acquiring the log in the same order. So this kind of example can be solved by metalog, and also we can do it with the trilog, and then also we can solve it as like having a total ordering. So you might think it as like I described about like 4 different cases of the deadlock, but with the single example, I can explain the 3 of them. Yeah, but how you can regard this is like that this kind of cases are not independent. So based on the cases, we can use different measures to resolve that. And then the more important thing is like that we have 4 different methods to resolve the deadlock. And then based on the case that causes deadlock, we can apply each of the measures to avoid that. Any questions? Yes.
What is the reason that we unlock we lock like set A and then we lock the second one and then set B, and then why do we unlock them in the opposite order?
So we don't have to unlock in the opposite order.
Okay.
Yeah,
okay.
it doesn't. Yeah, yeah. And then like I put it in the opposite order because like I lock the log 1, log 2, and then like it's something like a stack. The log 2 unlock first and then log 1. So I like intuitively write the code like that, but we don't have to do that. Yeah. So the reason why I did not explain about like unlock order is that is not that important for the deadlock condition. So the most of all the deadlock condition happens with the lock order. Yeah, that's why. Yeah. All right. And then the quiz 3 will be starting from tomorrow. Do you have a question? No. All right. Yeah. So you can expect that the sum of this kind of questions can be on the quiz 2, quiz 3, right? It's easy to make this kind of the questions, right? So that there will be some deadlock questions and also the mutex questions, and then also including some of the data races, and then including the lab 3 part mostly from JAWS. And then please take a look at the sample quiz, and then if there's an answer sheet, so please try to study about that. That might be definitely helpful for like the solving this kind of the concurrency bugs issues. And then like I borrowed a little bit of slide from the textbook slide, and also like I excerpted the code snippets borrowed from the textbook. So we do not use textbook much, but if you are curious about the details, please read the corresponding textbook part for that. All right, this is the end of today's material, and then good luck to quiz 3, and then feel free to ask any questions down here.